In today's lecture, I will show you that how to design the equivalent circuit of split ring resonator metamaterial unit cell on HFSS. This is the subsequent part of the video where we have designed this on ADS software. Now we are designing the equivalent circuit on HFSS itself. So today I am not going into the detail of how to design the equivalent circuit or what physics works behind the development of equivalent circuit. We have already discussed it in our previous video. You can get the reference from there. Today I am directly developing the equivalent circuit and then extract the parameter of variables. So in HFSS, when you will choose this window, here HFSS is shown, then Q3D, then circuit. So we have to choose the circuit. When we will click on it, this window will appear, then click OK. So in project manager, you can see there is a name circuit 3. You will found here, and a component library. By default, it will be open in the right hand corner. If it is not open directly, then go on the view and component libraries. Now from component libraries, we choose the combination of inductor and capacitors as we have chosen in the previous video. So I am taking capacitor. We have to require 3 capacitors. So 1, then by clicking Control R, it will be rotate, then copy and paste it, and again paste it. So we have 3 capacitors. Now we choose 4 inductors. 1, 2, 3, and then just copy and paste. By using connecting wires from here, we will connect all them. Now choose the ground. And apply the ports. It is input port and output port. So the circuit designing portion is completed. Now just open the project tree. Click on analysis. Just right click on analysis. Then add Maxim solution setup and choose linear network analysis. Here you will found in swap variables name frequency. Here swap is already written. So just double click on frequency. If there is something, make it delete, or if nothing is there, then you can directly provide the values. So our starting frequency is 5 gigahertz and stop frequency is 15 gigahertz because our splitting resonator was resonant at 13 gigahertz frequency and number of counts are 4000. Just add it. Okay, so you will get this value here, then okay. Now again right click on analysis and then click on analyze. After completing the simulation, select the result, right click, create standard report rectangular plot, choose S11 and S2, S11 and S21. Unit is dB. So this is the result. We are getting the 6.7 gigahertz resonant frequency because of these given values of inductor and capacitors. Now we have to tune or optimize our network to get the new values of L and C so that our S11 parameter should be resonant at 13 GHz. For tuning the network component, we will first make them variable. So just click on them and assign the value L1. Okay. Don't change in any value. Click OK. Similarly, it will be L2, then L3. It's your choice that how many components you want to make the variable. L4, then C1, C2, and C3. So in design properties, you will get L1, L2, L3, L4, C1, C2, C3. We make all these components variable. And now again, go on the circuit, design property, then local variable. In this window, first we will choose the local variables, then tuning. When we will choose the tuning, you can see that all these includes are open. So we will check them. If we check them all, that time we can tune all these parameters. Apply. Okay. Now just keep the result here. The optimetric, right click, tuning. So when we will click on tuning, this window will appear, and here you can see this should be unchecked so that we can make these parameters variable. By changing the value of L and C, we can tune the parameter. So here you can see that we slightly change the first inductor, and the frequency shifted at 13 gigahertz. Okay. Similarly, by shifting other inductor and capacitors, you can tune your network. Here you can see C2 is responsible for shifting the frequency band. Also, C1 is also responsible for shifting the frequency band. Okay. So by changing all these values, you can tune your circuit. Now it is resonant at 13 gigahertz. So we will save all these values. And what we will get, the all values are here. Now for optimization, click on circuit, design properties, local variable, choose optimization and optimize all variables. Then click on Optimetric, add optimization. So in setup optimization, we have several optimization algorithms. We will choose any one of them. So I am choosing adaptive single object, or we can choose gradient genetic algorithm. Then in setup calculation, choose S11 parameter in dB, add a calculation. Now our frequency is we can change our frequency range. It is right now 5 to 15 gigahertz. So we will choose it from 10 to 15 gigahertz. So now it is 10 to 15 gigahertz. Condition less than equal to goal. Add it as numeric value and choose -10. Okay. So now the calculation solution is linear frequency. The objective is make S11 parameter less than equal to -10 in between 10 to 15 gigahertz frequency band. Okay. Now click on Optimetric, analyze all. So here you can see that optimization process is going to be start. So here after completing the simulation, we can see that it is resonant at 12.50 gigahertz frequency band, and it is less than -10 in between 10 and 15 gigahertz. So what we have provided the goal, it is make it satisfied, and these are the value of L and C for this combination. So if we choose these inductance and capacitance value, our resonant frequency will be 12.50 gigahertz, and also it covers the 13 gigahertz band also. So by this process, we can make the equivalent circuit of any antenna or microwave devices. Thank you.